Welcome to the Solar System. The Sun is a star located at the center of the Solar System. It's an almost perfect spherical ball of hot plasma with a slight flattening, measuring only 9 parts per million. The Sun heats up to incandescence through nuclear fusion reactions in its core. It primarily radiates energy in the form of visible light, ultraviolet, and infrared radiation, making it the most important energy source for life on Earth. There are 8 known planets that orbit the Sun. These include 4 terrestrial planets, Mercury, Venus, Earth, and Mars, as well as 2 gas giants, Jupiter and Saturn, and 2 ice giants, Uranus and Neptune. The Solar System also contains 9 objects typically considered dwarf planets, along with many candidates, a main asteroid belt, numerous comets, and a plethora of icy bodies beyond the orbit of Neptune. 6 of the planets and many smaller objects have their own natural satellites, with the satellite systems of Jupiter, Saturn, and Uranus resembling miniaturized versions of the Solar System in some respects. The Sun is located near the inner edge of the Orion Arm within the Milky Way galaxy, at a distance of 24 to 28,000 light-years from the galactic center. It resides within the local interstellar cloud or Gould belt, a sparse hot gas region, likely created by multiple supernovae. The Sun and the Solar System are found in what scientists call the galactic habitable zone. The Sun has a radius of approximately 695,000 kilometers, which is 109 times the radius of Earth. Its volume is approximately 1.41 times 10 to the power of 18 cubic kilometers, or 1.3 million times the volume of Earth. Its mass is roughly 1.9885 times 10 to the power of 30 kilograms, making it 330,000 times the mass of Earth and accounting for 99.86% of the total mass in the Solar System. The remaining 99% of this mass is shared among the 4 gas giants of the Solar System, with Jupiter and Saturn alone accounting for over 90% of it. All other bodies in the Solar System contribute to less than 0.002% of its total mass. The Sun formed approximately 4.6 billion years ago as part of a massive molecular cloud predominantly composed of hydrogen and helium. This cloud may have also birthed many other stars. This conclusion aligns with radiometric dating of the oldest Solar System materials, suggesting that around 4.567 billion years ago, 1 or more supernova explosions occurred near the Sun's formation site. The shock waves from nearby supernovae compressed the material in the molecular cloud, causing certain regions to collapse under their own gravity, triggering the formation of the Sun. When a fragment of the molecular cloud collapsed, it began to rotate due to the conservation of angular momentum and warmed up as pressure increased. Most of the mass concentrated in the center, while the rest flattened into a disk, giving rise to planets and other objects in the Solar System. Accumulating more material from the surrounding disk, the core of the cloud generated a significant amount of heat, ultimately igniting nuclear fusion. The Sun is composed of elements such as hydrogen, helium, oxygen, carbon, iron, magnesium, nitrogen, silicon, and sulfur, among others. Its average density is approximately 1.408 grams per cubic centimeter. The surface temperature of the Sun is around 5,500 degrees Celsius, while the central temperature is a scorching 15 million degrees Celsius. In the core of the Sun, about 600 million tons of hydrogen are fused into helium every second, converting around 4 million tons of matter into energy in the process. This energy takes roughly 10,000 to 170,000 years to escape from the core and serves as the source of the Sun's light and heat. The average distance from the Sun's center to the Earth's center is defined as 1 astronomical unit, which is approximately 150 million kilometers. It takes about 8 minutes and 20 seconds for light to travel from the Sun's surface to the Earth's surface. This sunlight energy supports nearly all life on Earth through photosynthesis and drives our climate and weather systems. The Sun's structure consists mainly of the core, radiation zone, convection zone, and the atmospheric layers. The core of the Sun has a radius of about 20% to 25% of the Sun's radius, roughly 140,000 to 175,000 kilometers, with a density of 150 grams per cubic centimeter and a temperature as high as 15 million degrees Celsius. It releases energy at a rate equivalent to converting about 4.26 million tons of mass into energy every second, which is roughly equal to 9.192 times 10 to the power of 10 million tons of TNT. The Sun's core is the region where the majority of this energy is generated, with about 99% of it produced within the inner 24% of the Sun's radius. Beyond a radius of 30%, nuclear fusion nearly ceases, and the rest of the Sun is heated by this energy. As this energy travels outward through several successive layers, it eventually reaches the Sun's photosphere, where it escapes into space through either photon radiation or convective mass particles. The radiation zone, which makes up about 45% of the Sun's radius, approximately 313,353 kilometers, is the last layer. Heat radiation is the primary mode of energy transfer, and as you move outward from the core, the temperature decreases from 7 million to 2 million degrees Celsius. The radiation zone and the convection zone are separated by a transition layer called the tachocline, which is the region where the uniform rotation of the radiation zone transitions to the turbulent convection of the outer layers. The convective zone, which extends from about 0.7 solar radii to nearly the surface, is where the plasma density or temperature is not high enough for energy to be efficiently transported outward by radiation. Instead, the density is low enough to allow convection to occur, carrying the Sun's energy outward to its surface. Heated material absorbs heat and expands, reducing its density and causing it to rise, creating thermal cells that transport most of the heat to the Sun's surface above. Once the material diffuses and radiatively cools at the surface of the photosphere, its density increases, and it sinks back into the base of the convection zone, where it absorbs heat once again from the bottom of the radiation zone. This convection cycle continues, and by the time it reaches the photosphere, the temperature has dropped to about 5,700 degrees Celsius, and the density is only 0.2 grams per cubic meter. The visible surface of the Sun, known as the photosphere, is where the Sun becomes opaque to visible light. The photons generated in this layer escape into space through the transparent solar atmosphere above, becoming solar radiation, which is what we perceive as sunlight. The photosphere is tens to hundreds of kilometers thick, and its opacity is slightly lower than that of Earth's atmosphere. The Sun's atmosphere is divided into four parts: the photosphere, the chromosphere, the transition region, and the corona. The corona is a plasma halo around the Sun, extending millions of kilometers into outer space. It is easily visible during total solar eclipses and can also be observed using coronagraphs during non-eclipse times. Spectroscopic measurements show that the temperature in the corona exceeds 1 million degrees Celsius, making it a highly ionized plasma. The solar wind, composed of charged particles, emanates from the corona. The outermost layer, the heliosphere, is a thin atmosphere filled with solar wind plasma that extends into space for millions of kilometers. Ultraviolet radiation from the Sun has various effects, including disinfection of tools and water, causing sunburn, and triggering biological responses such as vitamin D production and tanning. However, it is also a major contributor to skin cancer. Ultraviolet radiation is strongly absorbed by Earth's ozone layer, resulting in significant variations in ultraviolet levels with latitude and contributing to various adaptations in living organisms. The Sun has a variable magnetic field on its surface, with the solar magnetic field extending far beyond the Sun itself. Electrically conductive solar wind plasma carries the solar magnetic field into space, creating the so-called interplanetary magnetic field. The effects of the Sun's magnetic field are collectively known as solar activity, which includes solar flares and coronal mass ejections, often occurring within sunspot groups. The Sun's slow-changing, high-speed solar wind streams originate from coronal holes on the solar surface, and both coronal mass ejections and high-speed solar wind streams carry plasma and interplanetary magnetic fields outward into the solar system. The impacts of solar activity on Earth include high-latitude auroras and disruptions to radio communications and power systems. Sunspots, also known as solar spots, are dark areas on the Sun's photosphere caused by intense magnetic activity suppressing convective activity. They form regions of reduced temperature on the surface, although they still have temperatures of about 3,000 to 4,500 K, appearing darker in contrast to the surrounding material, which is approximately 5,780 K. Sunspots are rare when isolated but tend to occur in clusters. They follow an 11.2-year activity cycle and can affect Earth's magnetic field during periods of high activity, leading to disturbances in Earth's atmospheric circulation at high latitudes, resulting in harsh weather conditions and even, in severe cases, damage to various electronic devices and appliances. It's important to note that observing the sun directly with the naked eye during periods of sunspot activity can permanently damage one's eyesight. Next is 133 days of intense solar activity. Thanks for watching, and if you liked it, please remember to subscribe, comment, and like.